Welcome to Complexity Made Simple. My name is Paul Allen, and the subject of today's video, we're going to take a look at a case study for one of my clients. Hope you enjoy it.
Okay, so here we go with a case study. It's an injection moulding case study, and what you're going to see is you're going to see a complete project from beginning to end in terms of getting the process under control and then taking the process to excellence. So you have to do control first, then you do excellence second, and because of that you're going to see a design of experiments and best settings discovered for an injection moulding process. So let's take a look at this thing. So here's the machine. One of the things they're trying to do, important thing, they're trying to increase the capacity on the machine. So the project, the central part of this project is not so much that they have defects. The defect rate isn't particularly large, as you'll see. But what they'd like to do is speed the process up. And there they go. Are we running as efficiently? We want to make sure that we're running as efficiently as possible. Are we at best settings? Yeah, so the machine's working to a lesser or greater extent, but is this the best it could possibly, is the best it could possibly be? So here's the part. It's a simple cover. It's approximately 8 inches long, and we want to try to reduce the cycle time by 15% if at all possible. We'd also like to try and get the CP kept to 167. So some basic analysis first of all, process flow. So here's the current process, and using the flow diagram, we're then going to discover all the variables in the process. Is the process under control? And this is the current state. So the current state, everything that's in amber here, these variables currently do not have a standard way, a standard operating procedure. So there is no standard machine maintenance, tooling maintenance, robot setting, etc. No standard way of dealing with the regrind, etc. So that's the current state. Everything that's in green currently, that's under control. And if you let those variables play into the process, here's the current performance. So this is the length of the part. Now you can see the length of the part is a very capable process. There's cavity 1. There's cavity 2. So in terms of length, we don't have a problem. But let's look at flatness. Flatness is a different issue. So flatness, look, is only just capable. Yeah, so the cavity 1 just fits in. So cavity 1 is not causing too much of a problem. Cavity 2, however, isn't quite as well centered, and therefore cavity 2 is producing us approximately 4%. So 4% of everything that comes out of cavity 2 is going to be defective. I think overall we're getting about 1.5%, something like that, 2% as the sort of defect rate, because this cavity here is kind of okay. So so it's not the biggest problem in the world, but what they'd like to try and do, they'd like to get that much better, but they'd also like to try and get the cycle time up as fast as possible at the same time. So let's go back to those variables. Now the first thing they have to do in order to be able to interrogate the machine and find best settings, because here is where we need to find best settings. So these things, injection speed, holding time, cooling time, etc., tool temperatures, all of those kinds of fine settings. The only way to be able to find best settings and to find best settings that work is first of all to establish a controlled environment into which those settings will be used. So first of all, we're going to have a look at the way the material is mixed. They come up with a new standard operating procedure in order to get that under control. So that turns green. then we go up here to the setting sheet. So if we're going to put standards in place, do we adhere to them? Yeah, so are they standards that everybody's going to use? There is no point coming up with the best settings if you have no method of applying them. So we come up with a standard way of controlling the settings. To go with that, there is also an audit procedure behind that to make sure that those settings are actually used. So now, if we do put the best settings into the machine, they will stay there. They will always be used. The robot setting, let's make sure that the robot has got some standards. So there we go. It's a standard way of setting up the robot. That goes green. Then we move on to the maintenance issues. Now, this is really important. If we don't keep good maintenance of tooling and the machinery, no standards, no settings will work properly. And your operators and your setters will constantly be searching for the right setting, given that everything else is moving around. So we need a tooling maintenance schedule. That goes green. We need a machine maintenance, and of course safety is in there as well. Very important, and that goes green. And then finally, are the measurements under control? Do we have a standard way of applying the measurement? You can appreciate that trying to measure the flatness of that long plastic cover is quite difficult. It would be very easy for people to come up with different methods. So we have to come up with a good standard repeatable measurement system for measuring flatness and length. And therefore we've come up with a standard operating procedure for that. And finally, what that leaves us with, of course, is these machine settings. Have we got the best machine settings? Have we got the machine at its fastest? Have we got the temperatures at their coolest? Are we running as efficiently as we could possibly make it? And also, can we get the CPK to be better? So we're going to use a tool. So having created a stable environment, now we can do a very deliberate testing system, a very deliberate test on the process, known as a designed experiment. Now the first one that it says there we're going to do is a screening DOE. That's because we have lots of variables and we don't yet know what they do. So here is the screening DOE. Now just before we take a look at the test that's conducted here, I want to just think about how complicated the problem currently is. Because what do we have? We have 1, 2, 3, 4, 5, 6, 7. We have 8 variables there. And you'd think, well, it's only 8 dials. It's only 8 settings. It can't be particularly difficult to find the best settings. Now I know that you can find settings that work on a machine. That isn't what we're trying to find here. We are trying to find the very best settings, the fastest settings with the best quality. This isn't about a set of settings that just work. They already have that. Okay, so we are trying to find the very best settings. So 8 variables. Now it looks really easy, doesn't it? But actually what most people do is they only count the variables. They don't look at the number of combinations. So look at this. You have 100 choices multiplied by 50 choices, multiplied by 44, by 44 choices, by 225 choices, by 90 choices, by 20 choices, by 400 choices. If you multiply that lot through, this isn't 8 variables that you're looking at. And I've just worked this out on a calculator. Oh dear. It's 1.5 trillion choices. That's the complexity of trying to find best settings. This cannot be done with someone's skill. Someone cannot carry this model in their head and understand what the best settings will be to get the fastest process with the best capability. It just is not possible. Only DOE can interrogate that design space, using mathematics essentially to interrogate that design space. One of the things I've included here, look, is regrind. Regrind is something that they don't currently control. Most companies don't control regrind, simply because you never know quite how much you're going to have. So it tends to be a movable feast, regrind. So we are going to put that into the test because we want to see what effect it has on our process. One thing that's very important when you do a designed experiment, this is a very structured procedure. This is not just random tests. You are about to see 12 tests. So the designed experiment of choice is known as a Taguchi L12. It's a pre-designed pattern, and it is a pre-designed pattern to get the most information in the fastest time. That's why we do these things. We don't do them just to be mathematically perfect. You get the maximum amount of information from the minimum amount of data. So it's a very structured test. It's not just an engineer making up 12 experiments. That's not what's going on here. Anyone that did the L12 screening DOE would do an exact same pattern on their moulding machine, on their packing machine, on a press, on a furnace, whatever it happens to be. The pattern is the same because the pattern is super efficient at getting information. So really important that we do a great procedure when we do this. You'll see how disciplined this team have been here in making sure that this DOE goes really well. Labeling all the parts. Very important that the parts are kind of well looked after, well labeled. All the data is important. If you miss one of these tests out, the other 11 are not as useful. So this is it's a very different type of testing to what an engineer would do, where he'd just simply have a guess, put some tests in, have a guess, do a test, have a guess, do a test. These tests all have to work together, so you have to follow the pattern. And here is the pattern. So there's the pattern. Key point about the efficiency here, as I mentioned, we have 8 variables, 8 settings. We are only going to do 12 tests, 12 setups, although obviously we are repeating, we are collecting a sample multiple times for that setup, but we're only going to set the machine up in 12 different ways. We've collected data on flatness because that's the area where we've got to understand how to get a flat part. Both cavities have been put together, as you see there. And we've also collected data at the same time on the cycle time. And here's the key point about this experiment as well. What this experiment is going to do is find the sweet spot. We want to go fastest with the best capability. Where is the sweet spot? That's what these experiments are going to tell you. Often you have engineers who know how to go fast. They can't get the quality. They know how to get the quality, but they have to slow the machine down. Where's the sweet spot? The sweet spot is so difficult to find just in your head. This is going to find the sweet spot for us. So out of that experiment comes some diagrams. For those of you that haven't seen these diagrams before, the marginal means plot. The longer these lines, the more influential the variable actually is. And what we often get is a graph that tells us how the variables move the average, how they shift the mean. That's what this is telling us. So for instance, the screw speed, look, has the biggest effect on the flatness. But it also tells us about the standard deviation. So do variables affect the spread? So does it affect the spread of this thing? So the mean, the middle here, wouldn't be moving. But the distribution of the results, the variability, is being reduced or increased. Now that is being driven here, look, by the holding pressure for flatness. So immediately we know how now to pinch the variability in for flatness. So they're the two graphs for, they're the two diagrams for flatness. And then we just have one graph for the cycle time, because of course the cycle time is completely repetitive. There is almost no variability in the cycle time whatsoever. It's computer controlled. But the biggest effect, you would expect these to be time related. Cooling time has a big effect. Injection speed, screw speed. They're all about speeds and times. They don't have an effect on the cycle time. So that's not too much of a surprise. But of course, we're trying to find the sweet spot. It isn't just that we know something. It's that we can find the best midpoint, the best settings. So as a result of those simple graphs, they've decided to holding pressure at 100, because that was the release variability for flatness. Screw speeds up at 200, material temperature 225, fixed tool temperature has gone to 14, and move-in tool temperature has gone to 60. So they fixed 5 of the variables just using simple graphs. Just took them 12 tests to figure that out. Yeah, so we've got the flatness now better controlled. We've got the cycle time going pretty quick. So looking good so far. Moving on, this leaves 3 variables that they haven't fixed. Regrind percentage, injection speed, and cooling time. Now these are going to go into what's known as a full factorial. A full factorial allows for a mathematical model to be created on the process. So rather than just using simple graphs like we just did, we're going to use some mathematics this time, because this is a DOE that allows that, a full factorial. So there's the DOE. Again, the pattern is important. They've reduced the high and the low down for regrind. So previously the high was up at 100%. They've decided to bring that in, and they've just gone to 50%, which is more likely to be what gets used out in production. So they've changed the design space slightly in the second experiment. So again, here's the data. Discipline test. We need to collect data on flatness. Only 8 setups, by the way. So let me just point out, we did a screening DOE. We did 12 setups on the machine. We've now done a further 8 setups. Okay, so a total of 20 setups. And from those 20, we're going to pick best settings from the 1.5 trillion that we had out there. This is a super efficient way of doing this. Cycle time and flatness. So again, we're collecting both of those, and again, we're looking for the sweet spot. Okay, and now what we have is a model. So for those of you that haven't seen it before, in this column here, that is an equation of how to achieve flatness based on regrind, injection speed, cooling time. The interaction between these two and the interaction between these two is also important. So we have a mathematical model. We also have a mathematical model for cycle time. it's going to be a hell of a lot simpler because typically speed and time are going to have a huge effect on cycle time. So the model on the right, not so important, but the flatness is a great model to have. We now understand the process really well. So what we're now going to do is ask the computer, now it knows those two models, we're going to ask the computer, to try and hit the two targets. So here are the two targets. We've asked it to come up with a cycle time which is less than 18 seconds. At the same time, we've tried to get a flatness which is less than 2.2 millimeters. So we've asked for those two things, and it said, you know what? Here are your settings if you want to achieve those two things. Let's have a look. So this was the before and this is the after. Look at the difference. Now we've put those best settings in. So we've put the best settings in from the screening DOE, the best settings from the modeling DOE. Just 20 tests have got us flatness that looks like that. That is just incredible, isn't it? Let's have a look at cavity 2. Now cavity 2, if you remember, was the one that was giving us the problem. Cavity 1 wasn't such a problem. So if we can achieve the same thing with cavity 2, then we're in good shape. Look at that. So now, process capability before, process capability after. Fantastic. We are pretty much defect free. And take a look at the numbers at the top. Look at the cycle time. The cycle time has come down by 4 seconds, 5 seconds. We've knocked 20%, probably more, off the cycle time, and we've increased the process capability. So let's have a look at the benefits. Now this is just the saving on manpower, but to be honest, it's probably a lot more. It's probably a lot more than this. Quality wasn't causing us a big deal. Look, it was 1.4% the old process, but now 0 defects. So we're going faster and better quality. So all the targets were met. We were aiming for 19.26 on the cycle time. We actually hit 17.49. We were aiming for the CPK of 167. We actually hit the CPK of 3. So we absolutely smashed the targets. We had 1.5 trillion choices. And we only ran 20. Only a DOE can find these answers so quickly. There we go. Total cost saving, 15.
Well, I hope you found that useful. If you've got any questions about that topic, or indeed anything to do with Six Sigma or Lean for that matter, give me a call and I hope to hear from you soon.